All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for your blessing, and thank you for your mercy to us, to help us to understand a little bit more about your creation together, and just to enjoy this time, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me dive straight in here. Somewhat picking up where we left off last time. If we have a frame, EI, we can write it as, the sum, let's say k equals 1 to 3 of AIK UK. So what this is saying is that the attitude matrix, right? Basically the attitude matrix, if you write it as a matrix, it has essentially, E1, E2, E3. If I think about these as the, let's say, coordinate vectors, just the, as numerical row vectors. Of course, we do want to think of EI and UK both as derivations on smooth functions from R3 technically. All right. So then here's a calculation we want to do. I want to calculate omega ij of V. All right. And remember what that means is the covariant derivative in the V direction of EI dot EJ. That's what we worked out last time. And so we can expand on that. Yeah. So we got what? We got, I'll just pull the sum out. I'm going to go ahead and pull the sum out just like that. So K, covariant derivative of V acting on AIK UK, like so, and dotted with EJ. All right. But you remember there's a product rule for the covariant derivative, and the product rule here gives us the sum over K of V acting on the function AIK times UK plus the plus AIK times the covariant derivative in the V direction of UK. All right. But remember what UK is. Like U1 is partial x1, U2 partial x2, right? U3 partial x3, or if you like XYZ. So these are not varying. So the derivative, those are constant vector fields, right? So the second term there is just 0. So this is 0. And, all right, so then what? So then, well, then we've got the sum over K of V acting on AIK. All right, and then UK dot EJ, right? So what is, I'll write that up here. What's UK dot EJ equal to, though? Well, that's really just UK dot, let's say the sum over, I'll use L, of A, let's see here, JL UL, right? That. But you see what happens is this and that just give you a Kronecker delta KL, and this simplifies to what? Just A. The L is equal to K actually, so we just get A JK. All right, so in short, the dot product of this with that produces me an AJK. All right. So then, let's see here. What's that? Well, this we could rewrite as like the sum over K, for instance, of A, J, K, D, A. Well, I don't want to do that either. Rats. Well, let me do this. Okay, so I'll make up my mind eventually here, guys. Oh, man. This board is not friendly to Spannoing. All right, so I guess I'll stick with it this way. So that's dA ik of V times A transpose kj, right? So that is what we would naturally interpret as, for example, we could write that as like dA wedge A transpose ij acting on V. So from this we find that omega is equal to apparently dA wedge A transpose. So we can write, so the connection forms, right, the connection coefficients rather, this omega ij, in principle, I guess there could be 9 of them, but we learned that they're antisymmetric last time, right? So that means that there can only be at most 3 of them, because there's 3 by 3 antisymmetric, only has 3 independent components. But we can think about them collectively as a matrix of 1 forms, right? A matrix of 1 forms omega, and that matrix of 1 forms can be obtained by the derivative of the attitude matrix wedged with the transpose of the attitude matrix. And last time, the end of class, we noticed that since A transpose is equal to the identity, we also have identities like dA wedge A transpose is equal to, like minus A wedge dA transpose. So we could also write this, or if you like, you could say dA is equal to like minus A wedge dA transpose wedge A. Or, I mean, there's a bunch of different things you could write here, but let me see what I want to write. Well, anyway, I'm content with dA wedge A transpose for now. Okie doke. Now, if you look at my lecture 7, I actually work out, what that actually looks like in detail for like the spherical frame and the polar frame. All right. I guess I can do the polar frame in class. I probably have time for that. I'll regret this. But here it is. So polar frame, basically, polar frame is, well, cylindrical frame would be this, right? Like E1 partial r, E2 partial theta, E3, not that, 1 over r partial theta for reasons of scaling, and then partial z. So the components of those with respect to the Cartesian basis are like cosine theta, sine theta 0, and minus sine theta, cosine theta 0, and 0, 0, 1. So then if you calculate dA, you get minus sine theta, cosine theta, minus cosine theta, minus sine theta, 0. I just took the luxury of factoring d theta out because it's everywhere. And then if you do, like dA wedge A transpose, in this case, you get, let's see here, minus sine theta, cosine theta, minus cosine theta, minus sine theta, 0, 0, 0, 0, 0, times A transpose, which was cos theta minus sine theta, I regret this, sine theta, cosine theta, 0, 0, 1, 0, 0, and I factored the d theta out because I can. And when you look at this, you get what? You get rats. I bet I did it wrong. Well, oh no, it's fine. Sorry, I was expecting something else, and what I was expecting is wrong. So, okay, so in short then, I get minus sine, cosine, plus sine, so like 0 here. And then, let's see here. Next, I get minus cosine squared plus sine squared, so I get a minus d theta here. And then I get 0. I get d theta. I get 0. I get 0. 0, 0, 0. So there explicitly is the matrix, the connection form matrix omega here for the polar frame. It's just that. So it's particularly simple. The spherical frame works out a little bit more interesting, kind of like your homework problem. Okay, so moving on here. If I can find my next thing. All right, where was the next thing? Oh, here it is. So I want to talk about Cartan structure equations. And so to do so, I need to introduce some notation. First of all, theta is going to be a vector of the coframe. Theta 1, theta 2, theta 3. And also we like to use d squiggle as the vector of the Cartesian coframe, dx1, dx2, dx3. Furthermore, when you study this, you'll find out that the attitude matrix, so the attitude matrix by definition relates the Cartesian frame and the non-Cartesian frame, like the EI to UI, right? It turns out, when you work it out, that the same rule goes for the coframe. It's actually true that theta I is equal to the sum j equals 1 to 3 of aij dxj. So you can compare that to my rule right there, right? EI equals the sum. I can change it to j just to make it look more like the same. J equals 1 to 3 of aij uj. So it's a little bit unnerving because so many times with these kind of things you end up with like an inverse matrix, but it's just not the case here when you work it out. Okay, so and those things are worked out in the PDFs that I posted, guys. But I didn't think it was interesting enough to talk about in class, like to show in class. I just talked about it after all. But so like, what this means then, in terms of this notation, is that theta is equal to a d zeta, or d squiggle, whatever that thing is. Yeah? Using the matrix of forms notation.
It's the same one?
Yeah.
All right.
Use your imagination. If you want, I can change the symbol. Anyway, Cartan structure equations simply state this. They state that d theta is equal to omega wedge theta, and that d omega is equal to omega wedge omega. These are Cartan structure equations, number 1 and number 2. I think we can derive these. Let us do that. So we just derived a formula for omega, right? So let's work it out. We have that omega is equal to, in terms of the attitude matrix, dA wedge A transpose. Oops. All right. So let's see here. And we also have this. So let's work on number 1. So, all right. So this right here, that gives me d theta is equal to dA wedge d squiggle plus A time wedge d of d squiggle. But what's d of d squiggle? D squared of anything is 0. All right? So that's just dA wedge that. But that is the same as dA wedge A transpose A wedge d zeta, d squiggle. And that is omega wedge, wedge theta. So this is that, this is that. Yeah. How about the other one? So there's the proof of 1. 1 is done. Now the proof of 2. D omega, what do we got there? We have D of dA wedge A transpose, right? We use the product rule for matrix, the wedge product of matrices of forms. And that gives us D dA wedge A transpose. And then what happens when we have to pay attention to the degree, right? There's a plus minus 1 to the degree term in so since this is a 1 form, I have to do minus dA wedge dA transpose. All right? Now the first term is 0 because again it's d squared, right? And the second term sorry, I need to remember what it is we learned last time in terms of what do we have? We have so I've got minus dA wedge, I guess I can insert an A transpose here, A wedge dA transpose, yeah? And so, well, the dA, I just inserted an identity matrix in the middle, as is my right. This right here is an omega, so I've got minus omega, and then wedged with, well, let's trade that for dA transpose wedge A. If I do that, I just switched the order, and that doesn't cost me anything. Or wait a minute, does it? Hold on a second. Can I do that? Let me not do that. I have a bad feeling about that. Let me not do that.
Where's the omega coming from?
Oh, that, okay, cool. Yep. So, yeah. Let me just think about this for a second. I've got A wedge dA transpose. All right, great. Let's remember what we have to work with. Since A transpose A equals to I, we have that dA transpose wedge A plus A transpose wedge dA is equal to 0. So let's see here. But I also have, it is also true that, A transpose is equal to I. So I also have that dA wedge A transpose plus A wedge dA transpose is equal to 0. I don't know if that's different, but it feels different. Well, it's a little bit different. So if I use what? If I use that one, if I use this one right here, that one's nice, right? Because that allows me to trade A wedge dA transpose for minus dA wedge A transpose, yeah? The minus and the minus cancels, and we've got omega wedge omega. Because dA wedge A transpose is omega by my calculation at the start of class. These are Cartan structure equations. What they're doing is they're telling us how the connection form, the change in the connection form, right, is related to the connection form. Apparently it's the wedge product of the connection form with itself. That's cool. And also how the evolution of the coframe goes is given by the wedge product of the connection form with the coframe itself. They're both very interesting relations because they say that the derivative has something to do with wedge product algebra with the frames, yeah, the coframes.
Am I wrong in saying that anything wedge itself would be 0?
Usually that would be right. However, these are matrices. So the wedge product of a matrix with itself, even though it's a one form, doesn't have to be 0. Excellent question.
Are we basically generalizing?
That bothered me for a time. What's that?
Are we generalizing the theory of K-forms?
Now we're talking about matrices of K-forms, yeah. So they have many uses. So like, for example, the connection on a principal fiber bundle. A principal fiber bundle is a fiber bundle over a manifold where the fiber is a Lie group. And if you want to talk about a connection on the Lie group, connection on the principal fiber bundle, it turns out to be the structure of it is a Lie algebra valued one form. So you could naturally think of it as a matrix valued one form. That's a place where, I think that's essentially the abstraction of what we're doing here. But that's for another course. I'm just saying it comes up past here. It's not just a, hey, let's find weird ways to use differential forms to do calculus in R3, Although it is that. But I'm content with that. All right, so let's go on. Again, in my lecture, let's see here, 8, I think it is. In lecture 8, I actually work out a few of these and show you how you can calculate them. I guess well, I don't know if we got time. No, I better behave. Let's go on. There's an example on page 10 of lecture 8, which actually shows you how to use these equations to calculate the omega. See, it's a pretty straightforward how to calculate d theta, right? And you can, by process of like wedge product structure, figure out what omega should be on the basis of what d theta and theta are. So that's kind of a more circuitous path to calculating the connection coefficients. But if you think about how we had to do it last time in terms of calculating covariant derivatives, it's kind of better. So if you look at page 10 again of lecture 8, there's an example there. If we have time, I'll show you today, but I'm going to go on because I ran out of time last time and it's annoying. So hard segue. This is just we'll come back to this stuff eventually, guys, but it's going to be a minute. So the next story arc in the course here has to do with what's called the shape operator. So we want to talk about a surface in 3 dimensions. All right, so just context here, what we're doing. This is, we talked about this in Calculus 3, for example. You had to do that because in order to set up, surface integrals, you have to describe a surface. So basically, if we have a surface in R3, what's it look like? I mean, whatever. I guess to be general, I should throw in a hole, as is there. Now it's a better surface, right? But the more interesting aspect here is we can define a surface, at least an oriented surface, as having a unit normal field, yeah? So we use U for that. Now, if a typical point here is given by x of uv, that's like a typical notation in the notes that I've written here, the parameterization of the surface, right? So that's a typical element of the surface, which is a 2-dimensional manifold, some manifold of R3 in terms of our language in this course. Then how you calculate U, you may recall, is you do what? Partial x, partial u cross partial x, partial v, right? That gives you the cross product of like xu and xv, right? Those are the partial velocities. You take the cross product of those, they give you the unit normal. Great. That's a surface in R3. And so let's define the shape operator for such. Here it is. Definition. If P is an element, I guess I call this SM. Let me call it M. For manifold, I guess I'll call it M. So let me stick with that. If P is an element of M, then for each P, for each V in the tangent space at P to M, let SPV equal to minus the covariant derivative in the V direction of the unit normal at the point P. I will soon prove to you, we'll show shortly, that SP is in fact a mapping from the tangent space to the tangent space. That is not immediately obvious because the covariant derivative generally outputs a three-dimensional vector, right? Why should that be tangent to the surface? It's not immediately clear that that should be the case, but it is. It's also not immediately obvious, perhaps, that that's a linear transformation, but in fact it is. In fact, the shape operator is a linear, in fact, indeed, a symmetric transformation on the tangent space. And by symmetric, I mean that the transpose of its matrix is equal to the matrix again, right? Okay, so the proof of that simply rests on going back to our identity for the covariant derivative. Remember how this goes? If we take V on u dot u, what goes on there? So we know u dot u is 1 by construction. It's the unit normal. So by this short Manga style calculation, that's 0. But on the other hand, it is u acting on V dot u? I've forgotten my properties already.
What is the name of the operator? The shape.
Shape operator, yeah. And I did this wrong. I mustn't. Covariant derivative is what it was. It was the covariant derivative in the V direction of u. Dot u plus u dot the covariant derivative in the V direction of u. But what's that say? That implies that the covariant derivative in the V direction of u, in fact minus it, right? Dot u equals to 0, which says that SP of V dot u is equal to 0, which says that SP of V is an element of the tangent space at V, of M, right? Which of course is the perp to u anyway, right? It's the perpendicular to the unit normal at the point P, for what it's worth. If you'll allow me that brief digression into linear algebra notation. So hey, it's in the tangent space. So you guys agree? Okay. Yes, no? How about linearity? Linearity is manifest from a property of the covariant derivative, right? So because this was linear, it follows that the shape operator is a linear transformation. So the shape operator is a linear transformation from the tangent space to the tangent space. And its construction is based on the change of the unit normal, right? So you can start to understand why this would tell us something about the shape of the transformation, because it's basically quantifying how the surface is bending as you go from point to point. Yeah? Now, let's see here. Let me see if I can actually calculate one of these things. I think I mustn't digress too far into here, because there are like slick formulas for calculating these things in the next lecture. So I don't want to devote too much time to this, but maybe we could figure out the shape operator. Maybe we could figure out a nice formula for like the unit sphere. You guys help me out here. So if I have, well, not the unit sphere, sphere of radius r, right? So like, you know, that's not. I don't want radius r. Yeah. So if I want to find what's the formula for, you know, the unit normal. Can you guys tell me? How about this? It's at the point P. We just do. I mean, forget about the point P. Let's just write down the formula. It's nothing more than what? It's like R, right? Divided by what?
Big R.
Divided by big R, right? So, like, so here is the center, right? So this point out to here is R, right? So if I just take this vector right here, so like, what's the length of this? Right, it's the length of R divided by R, which is R over R, which is 1. Okay, so that's a reasonable construction. So there's the unit normal on the sphere. So particularly u of xyz is equal to 1 over r xyz. So we can calculate the covariant derivative in the like whatever direction, right, of u is what? So it is given by, let me make a capital V so it's not like, so it's v of x over r u1 plus v y over r u2 plus v z over r u3, going back to last lecture. But what does that do? That just picks off respectively the x, the y, and the z components of the vector field big V. So it's straight up like, let me say, you know, like v1 over r u1, v2 over r u2 plus v3 over r u3, which if you tilt your head and squint for a second, you can see that there's a formula there. What is it? Like, you could factor the 1 over r out, and then what would you have? Yeah, v1 u1 plus v2 u2 plus v3 u3. What's that? This board.
U1 is 36. Isn't that just V?
Yes. Thank you. So that is just 1 over r times v. In other words, this is the identity transformation times divided by r acting on v. So what's this all mean? Well, this tells me then that the shape operator here in this particular instance, it's typically unpleasant to actually do this kind of computation for other surfaces. Like, this is generally unpleasant. But it could be done. Anyway, here's the formula for the shape operator on the sphere. SP of V is equal to minus 1 over r V. So no matter, so like, there you go, that's the shape operator. Now, yeah. All right. So let me tell you some stories. I'll spare you the calculations on the next example. Next example's not so much. Oh, did I never change it? Oh man. Well, sorry, Hefe. Jeff. There we go. I'll even zoom in for you. We've been mostly lately focused on this piece right here. I'll leave it there for a second while I'm erasing the other board. So we could engage in this kind of calculation for the other examples. And there is some of that in the PDF that I'm working out of, which is differential geometry, lecture 15 of my differential geometry playlist. But there's a better way. The computational methods to calculate what we're actually interested in are way better in the next lecture. So we're going to wait for that. We're not going to invest our too much time in this style of calculation here. But I do want to share with you just quickly what happens for a number of surfaces, just to give you a sense of it. So there's four cases, which I will collect: sphere, plane, cylinder, saddle. And we just worked out the shape operator for the sphere. All right. What you guys can probably tell me how it's going to go for the plane, right? What do you think the shape operator is for the plane? Like this I could actually work out as well. It's 0, right? Because the unit normal is what? It's constant. So if the unit normal is constant, shape operator is 0. Yeah. So for the sphere, the shape operator is just given by minus v over r. For the plane, the shape operator is 0. For the cylinder, I have to introduce like directions, but let's say E1 is equal to 0. And I think I use a little E1 for reasons. I'll stick with those. I don't remember them. But little E2 is actually minus E2 over the radius of the cylinder. And then the saddle is kind of funky. It, at the point P, of course. A saddle surface, when you can find directions, so the SP of E1 is E2, and SP of E2 is E1. I worked that out. Now you might wonder what on earth that means. So you guys know what a sphere looks like, roughly speaking. Plane, simple enough. Cylinder, one of these guys, right? I'm talking about this being R. A saddle is one of these things. All right. So this is actually z equals to xy. So you could work out the parameterization. Z of xy is equal to like xy. And I do that in the notes. I actually calculate the shape operator. And the E1 is, I think, just x hat, and the E2 is just y hat. All right. So the matrix of the shape operator, what's it look like here? The matrix is just like minus 1 over r, minus 1 over r. Here, the matrix of the shape operator is the 0 matrix. Here, the matrix of the shape operator, using E1 and E2 as the basis, okay? It's 0, 0, 0, minus 1 over r. All right? And the matrix for the shape operator of the saddle surface at a particular point, I don't think this is always constant. I feel like, well, and that's what I say. It's 0, 1, 1, 0. All right.
What they use in Riemannian geometry?
Riemannian geometry? No, this is not that. These are, this is in some sense, I don't know what to say this is. This is a, this is classical differential geometry, the differential geometry of surfaces, although the formulas that we're currently looking at are not classical, in the sense that these are not the historic formulas of Gauss. The historic formulas of Gauss are found in lecture 16, which I'll soon get to. Those give us nicer formulas. I don't know who originally did these things. I'm not sure the history of it, but it's kind of an overlay of what Gauss looked at in terms of like a more, I don't know, is this first in O'Neill? I don't know what the history of this particular formalism is, honestly, Ernesto. But, so what, you guys tell me, what could you choose for the shape operator independent of your choice of basis for the tangent space? You've got a linear transformation from a two-dimensional space to a two-dimensional space. What two quantities are independent of your choice of coordinates on the space that describe something that's intrinsically geometric about the transformation? What are those two things? Well, there's more than two things, but two things that are most interesting, perhaps.
And you said we're mapping from what to what?
We're mapping from tangent space to tangent space. It's a surface, so it's from R2 to R2, essentially. But you could choose different tangent vectors to set up your tangent space, you know? So the formula for the shape operator would look different in those different choices of coordinate, except for this one. This one always is 0. Maybe this one too. It's always that. But this one would look different if I chose a different basis. But here's the thing. So the determinant is an invariant, right? And what else is an invariant? The trace is an invariant. The determinant is actually, by definition, the Gaussian curvature. The trace is the mean curvature. Mean curvature. So I'll write it in red. The Gaussian curvature for the sphere, K, is 1 over r squared. The Gaussian curvature for the plane, 0. The Gaussian curvature for the cylinder, 0. The Gaussian curvature for the saddle surface, which I can't draw well, minus 1. Negative Gaussian curvature, 0, 0. Positive Gaussian curvature. Mean curvature. Well, the mean curvature of the sphere is what? Minus 2 over r, apparently. The mean curvature of the plane is 0. The mean curvature of the cylinder, minus 1 over r. The mean curvature of the saddle surface is 0. Now, so to understand curvature more deeply, we also introduced something called the normal curve. Let me define it over here. When I teach a standalone course on this, the thing I'm about to talk to you guys about, I would spend like a whole lecture on, but I just want to give you a sense of it. All right, we're not going too deep into this material, so we'll be okay with not knowing too much about it. But I want to let you know enough that you have a sense of it. And so the next definition here is called normal curvature. I guess there's also an identity we're going to need in order to understand where the formulas come from in the next bit of the story here. So So here's the definition. Let U be a unit tangent to M, which is a surface of R3 at P. Then we define K of U to be the shape operator acting on U dot U. This is the quote-unquote normal curvature. Normal curvature of M in U direction at P. So this basically, if you want to picture it, we have a notion of curvature from our discussion of the Frenet-Serre frame on a curve, right? And so we know how to calculate curvature of a curve. And this is kind of getting back into that. So like if I drew a picture, attempt a picture here. If we're at this point P, and perhaps we've got, let's see here, I think I tend to use I think I call it sigma. I'm a little fuzzy on the notation here, guys. It's not sacrosanct or anything here, I don't think. But yeah, I think we use sigma for, sigma is the curve. Sigma is the curve on the surface, which takes U as its tangent. Yeah. Little u. And then big U is the unit normal. Then if you want to think about it, you can think about it like as a little plane where you've got the unit normal goes this way, right? And U goes this way. And then sigma is just a curve in that plane, right? And so then you could calculate its curvature in the sense of two-dimensional curvature of curves. So it turns out that this is the so-called normal curvature. And let's see here. Well, again, I must resist the temptation to get too far into this. Let me just state a lemma, which we'll probably need shortly. Lemma 2.1. So this is on page 6 of my lecture 15, if you're keeping score. But this is lemma 2.1, which is if alpha is a curve in M, then alpha prime prime dot the unit normal is equal to the shape operator acting on the velocity dot the velocity alpha dot alpha prime. That's pretty cool. It means that there's a connection between second derivatives and the shape operator. Yeah. All right. The other definition I should share with you, this is kind of important, is that the max min values of K of U at P, really? Oh, I can't pick that up right now. That's unfortunate. All right, K of U at P. They're denoted like K1 and K2, all right? K1 is greater than or equal to K2. All right. These are the so-called principal curvatures. And the direction in which they happen are the principal directions. All right, so like, for example, on the cylinder, if we have, you can think about like the circle, right? So, and think about the line. So at this point, this gives us K of, I don't remember, I guess I'm trying to stick with the notation I used. E1 and E2 are principal directions actually for my cylinder example on the far board. So like I've used E1 for the upper direction, I guess. So like K of E1 is equal to 0 this way. This is E1. E2, K of E2 is equal to, oh man, I did bad. Minus 1 over R, I think. Ugh. Well, rats. Did I have a minus in there? Well, I've violated my condition. Oh wait, or have I? Oh, K1's greater than K2, woohoo! Everything's okay. This is K2, this is K1, and if I could do inequalities for a second, K1 is bigger than K2. K2 is negative, so haha. All right, there we go. But these are the principal directions on the cylinder. We can pick up on those kinds of directions by looking for maximums and minimums of the shape operator, which actually are going to be eigendirections. You see? Because it can be proved that, well, check this out. So if I do, so we can use the partial derivatives in these directions for basis, right? For TPM, yeah? So if you look at that, if we were, for instance, to take, that is, XUU is like this. It's like alpha of V, we could think of as X, X, let me stop. I don't have time to fix what I'm about to do. So moving on. So this gives us that like S of XV dot XU is equal to U dot XUV, and S of XU dot XV is equal to U dot XVU. So it is applying this lemma to this under the appropriate interpretation. See, so like, did I write down wrong? Well, I also have, on the step above, I have 0 is equal to partial V of the unit normal dot with the partial derivative. This makes sense. This is the partial velocity. That's the perpendicular to the partial velocity and the other partial velocity. So of course this is 0. But then by a product rule, this is also equal to partial U partial V dot XU plus U dot XUV. And then I said that this can actually be understood to be minus S of XV. So that's what's going on here. That right there is that, which is how I got well, anyway, so then this, let me stop this. I'm not getting anywhere. So I'm trying to explain page 9 on this thing, but it's going poorly, so let me just bail. The bigger point here, all I'm trying to tell you guys from this is it can be shown. I don't think I've shown it, but it's your homework, so you'll fix it. All right? So maybe don't fix it this way. But through some reasonable calculation, we can prove that the shape operator is symmetric. But if the shape operator is symmetric, then the real spectral theorem applies to it. It says it can be diagonalized. The eigenvalues are real, and there can be chosen, the eigenvectors can be chosen to be orthonormal, which is to say that there exist principal directions on a surface because the shape operator is symmetric. Now, they don't have to be unique. There could be infinitely many choices of orthonormal, like the sphere. Any choice, you know, but let me put this calculation out of its misery. Let's move on here. Now, there are surfaces which have both positive and negative curvature. Another important formula we can derive is this shape operator on V cross product with the shape operator acting on W is actually equal to the Gaussian curvature at the point in question times V cross W. That is not an easy thing to show. And it's also true that the shape operator on V cross product with W plus V cross the shape operator acting on W is equal to 2 times the mean curvature times V cross W. So these are nice formulas to know about. They relate, yeah.
Should there be a point?
It's all at P. It's all at P. It's all at P. Yeah. There are also formulas for the mean curvature. So it won't take a second to write them down, but like the principal curvatures, K1 and K2, they are given by the mean curvature plus or minus the square root of the mean curvature squared minus the Gaussian curvature. So there is this circle of interrelations between the principal curvatures, the mean curvature, and the Gaussian curvature. They are related. Another thing I should mention before I leave this lecture in the dust here, definition, surface M is flat if the Gaussian curvature is 0 on M, and the surface M is minimal if the mean curvature is 0 on M. So if you go back and you look at my list of 4 central examples, you'll see that the sphere is neither flat nor minimal. The plane is both flat and minimal. The cylinder is flat but not minimal. And the saddle was not flat, but it was minimal. All right? So, just enough time to get into trouble. The next lecture is a wall of formulas. These are how you actually calculate the Gaussian curvature. And it turns out, see, because like, you know, if we actually had to do the linear algebra here all the time, it would be troublesome. I mean, it's not impossible. I've laid out a method to calculate the shape operator, so you can pick a basis, you can calculate it, right? But it is a kind of lengthy calculation, you know? What I'm about to show you, though, is pretty cut and dried and, like, relatively easy to calculate everything in sight directly from the parameterization of the surface.